where we left off, we were comparing the instantaneous rate to the average rate, talking about the limitations of the average rate being that it is not quite so useful because the average rate depends on the amount of time that a reaction has proceeded, and so it's not a constant for any given reaction. The instantaneous rate, on the other hand, because it's concentration dependent, it is much more useful. And after comparing instantaneous and average rate, I walked you through kind of an explanation of where the instantaneous rate comes from, and we came up with this equation down here where the instantaneous rate was directly proportional to the concentration of a reactant, because when the concentration of our reactant is high at the beginning of a reaction, the rate is going to be high, and when the concentration is low, the rate is going to be low. And so what I did not do up here was write our equation for the instantaneous rate. The rate constant, little k, times the concentration of our reactant, A. And this term, rate equals Ka, we call the rate law. And so that's what I would like to talk about next. The rate law is the equation that gives us the relationship between the rate, the instantaneous rate, which, again, as a reminder, when I just say rate, when chemists just say rate, they are almost always referring to instantaneous, not average rate. So this is the relationship between the instantaneous rate, the rate constant, which is our little k, and the concentration of our reactants. And so let's write a generic rate law from a generic equation for this little a plus little b, which you've seen many times. As a reminder, the little letters are the stoichiometric coefficients, and the big letters are representing the molecules, the reactants and products. For that reaction, the rate law would be rate equals the rate constant, K, times the concentration of our reactants. So our reactants are A and B. Concentration of the reactants, leave a little bit of space there. And each reactant is raised to some sort of exponent, which I'm going to call X and Y. If we had another reactant, we just keep going with those letters. So they're raised to an exponent, X and Y, and notice that I'm using a different letter. I'm not using little a. I'm not using little b. These exponents, X and Y, are not the stoichiometric coefficients of the reaction. So X is not the coefficient for molecule A, and Y is not the coefficient for molecule B. And this is something that is really, really confusing for a lot of students. And one of the reasons why it is so confusing is because many times the numerical value of X and the stoichiometric coefficient are the same. So if little a is a 2, there's a pretty good chance that X is also going to be a 2. But they're still not the same. They're not the same number. X does not come from A, and Y does not come from B. So try to not let that confuse you. X and Y are called the orders of the reaction. So the X and the Y, and if we had a Z, these are called the orders of our reactants. So X is, in this rate law that we wrote, x is, we call it the order of A. Y is the order of B, and so on. The word order, as we use it in kinetics, doesn't have anything to do with like sequential order, like what happens first, what happens second. It's referring specifically to the actual reaction itself. So when the A and the B molecules are coming together and mingling, the exponents, x and y, are letting us know how many A molecules actually have to bump into each other, interact with each other in order for the reaction to proceed. And it gives us kind of an information of how the reaction actually takes place. So let's look at an example rate law. Example. Rate equals little k F2 ClO2. So for this rate law, and notice I'm not giving you a balanced equation to go with this, because the balanced equation is not used to come up with the rate law. We're just going off the rate law all by itself. So for this particular rate law, we could say that this reaction is first order. The phrasing that we use is first order with respect to F2. That is because the exponent over here for F2 is a 1, and so the reaction is first order with respect to F2, and also it's because both of the exponents are 1, it's also first order with respect to ClO2. And this is just letting us know a couple of things. It's letting us know how many F2 molecules and how many ClO2 molecules actually have to interact in this reaction. And it's also giving us some information about the relationship between the concentration of F2 and the rate of the reaction, because the exponent here is a 1. As we increase the concentration of F2, the rate of the reaction is going to increase at the same amount. Another thing that we can say when we're looking at this particular rate law, another thing we can say is the overall order of the reaction. So the overall order for any reaction is going to be the sum of all of the exponents in the rate law. So for this rate law, we have an exponent of 1 and an exponent of 1. So this particular reaction is second order overall, 1 plus 1. One of the useful things about the rate law is that we can use it to determine the rate constant K. So if we know the rate law, we can use the rate law to calculate K. We can use the rate law to calculate a lot of things, but we're going to start with K. So let's keep using the same rate law. We have rate equals little k F2 ClO2. And then let's say that we knew if we set this reaction up, and we would control this as the chemist, we would say let's start with 0.1 molar F2, or just some number that we chose. And let's start with ClO2, let's start with 0.01 molar of ClO2. So we would get those two reactants together in those specific concentrations, and then we would measure the rate of the reaction, and we would watch how fast it proceeds. And let's say that we determined that the rate of the reaction was 1.2 times 10 to the minus third, and the units of this would be molarity per second. So first, I want to add as a side note that the rate for this reaction, and for any of these reactions, totally depends on your initial concentrations of things. Like that's all three of these pieces of information need to go together. So let's use this data to calculate K. And this is literally as simple as solving for an unknown variable where K is our unknown. So we're going to say that K is equal to the rate divided by F2. This is just algebra, ClO2. We're just rearranging that equation to isolate the variable that we're trying to solve for. And now we're just going to plug stuff in. 1.2 times 10 to the minus third molarity per second over 0.1 molar, that's our F2 concentration, and 0.01 molar, that's our ClO2 concentration. And then we're just going to do the math on that. 1.2 times 10 to the minus third divided by 0.1 divided by 0.01. And we're going to get a rate of 1.2. Let's think about what kind of units we have here. One of our molarities will cancel out, so we end up with units of 1 over molarity second, or another way to write that would be 1.2 molarity to the minus 1, second to the minus 1. Kind of looks cleaner, but whichever one you would prefer. And so that's it. Now we could use this information again, now that we know this, now that we know K, because K is a constant as long as we don't change like the temperature or something. Now that we know K, let's calculate what would the rate be if we change the concentration of ClO2. So ClO2 concentration, let's say that we quadrupled it. So it's 0.04. And we'll keep the F2 concentration the same. So again, this is just going to be another algebra problem. We are using our rate law again. Rate equals K F2 ClO2, and this time the thing that we're trying to solve for is rate. What would the rate be with these new conditions? So our K, which we solved up here, 1.2 molarity per second, or per molarity per second, same F2 molarity, 0.1 molar, ClO2 molarity, 0.01 molar. One of our molarity units will cancel. And what do we get here? 1.2 times 0.1 times 0.01, that is going to be, what did I do wrong? I plugged in the wrong concentration for ClO2. We are going to get 0.0048 molarity per second. So this would be the new rate if we change the concentration of one of our reactants.